Okay, let's talk about average atomic mass. So this is a weird thing. You see the word average, and you might say, okay, well, I can do an average. That's pretty easy. But this is not a straight average. This is a weighted average. Weighted, which means that it's going to be weighted towards the percentage that's the highest abundance. And that's what you can see here at the formula. You can see that we take the percent of the isotope that we're looking at times its mass. So we have to take into account the percent abundance of that isotope when we calculate the average. Okay, this is the formula we use. You might see other formulas in other places on the internet, but I think this simplifies it pretty well. We're just going to take the percent times the mass, the second percent times the second mass, and we're going to do this with however many isotopes we have. And then at the end, we will divide our answer by 100 to get uh, rid of the percent, basically, to get the average atomic mass. Okay, so for problem number one here, we're dealing with copper. Copper is on your periodic table. This is the number we're trying to get, something close to that number, this average atomic mass right here. So copper 63 is 69.17% abundant. Copper 65 is 30.83% abundant. So right away we know a couple things. We know it's going to be weighted more towards copper 63 than 65 because 63 is a higher percent. And we know it's going to be between 63 and 65. So somewhere between those two isotopes is where it's going to be. So let's do a quick problem here. Let's plug in these numbers and see if our average pans out here. So percent times the mass. So my first isotope is 69.17%, 69.17% times the mass, which is 63. And it's very important that you do this first. So we're going to put it in parentheses to remind us to do this first. Okay. So next step here, we add it to the next isotope with its percent. So parentheses again, 30.83% times its mass, which is 65. All right, close parentheses because we want to do this first. And if we had more isotopes that went into calculations here, we can just do a plus sign and add more. We can keep on going forever if we want. But that's it. That's all we have. So to show that we're going to get rid of these percents, we can divide this whole thing by 100 to get rid of the percents. And that's how these problems work. And right away now we know that two things are going to happen here. Okay, we know two things are going to happen. We know that number one, let's see if I can type these here. Number one, we know it's going to be between 63 and 65. We can make this even simpler, right? We can say it's going to be between the lowest and highest masses. Okay, so that's one very simple thing that we can remember when we do these problems. If your answer is not between the lowest and the highest, it's not correct. And then the second thing is that it's going to be closer to the mass with the highest percentage. And instead of saying percentage, we can talk sciencey and we can say the highest abundance, because this is another way to kind of say the same thing basically. Okay, so let's go back to this here and let's see. Gotta switch back to my layer here. There we go. Let's see if we can finish off this answer here. Let's see if we can finish our calculation. So in the calculator, we would do this part first. We would figure out whatever this is. We would add that to whatever this is. And then finally at the end, we divide and we should get a number that's this or pretty close to this. And I think with just these two isotopes and just these abundances, I think we get 63.61 as our answer, which is pretty close. There's other factors that go into this number right here, including isotopes that might be slightly radioactive and things like that. So while we won't match exactly this number, we're going to get pretty darn close, and it looks like we did. Okay, one more quick thing. The unit for this, because we love units in chemistry, the unit for this is AMU, which stands for atomic mass units, which we've covered in previous lectures and videos and things. But 63.61 AMU is our answer. And it turns out, yes, check, right? It's between the lowest and the highest. That's true. And check, it is closer to the mass with the highest abundance. So we're looking very good. Average atomic mass.